Okay. The timer started, so I guess that means I am on. I only have 40 minutes, and I think I have the record number of slides when I submitted these, so we're going to go fast. I would encourage you to ask questions along the way, as long as they're short ones. Otherwise, we're not going to get through this, and then you won't get to eat lunch, which is no fun. So this is Knowledge from Noise, Geospatial Analytics at Progressive. And what I want to talk about is how Progressive thinks about location data and what it means to us. So who are we? Progressive Insurance. We're the fourth biggest auto insurer in the United States, and everybody knows this young lady. So does anybody not know who this is? I mean, Flo is everywhere. So she's kind of like our brand mascot. Everybody knows exactly who Progressive is when we talk about Flo. We're located in Mayfield Village, Ohio, which is just outside of Cleveland, so go Cavs. And a lot of things that you see here are built in Progressive's Business Innovation Garage. So here's a little peek inside of it. I have one of those messy desks in there. In here is where we build a lot of the new cutting edge type things that we roll out to customers not long after that. So that's our Innovation Garage environment. We also have a lot of different insurance offerings. We're more than just this. And most people think this is what Progressive is, an auto insurance company, but we have all these other offerings as well. And some of these I had to look up. I didn't even know what Mexico insurance was. Does anybody know what that is? It's like a special, Cindy knows, of course she does. So yeah, we have all sorts of products. But I want to talk today about Snapshot. And you saw a little bit of this at the keynote today. This is going to be a little bit more in depth about what Snapshot is.
Great suckers. Your car insurance goes up because of their bad driving. People try all sorts of ways to get rid of them. If you're sick of paying more than your fair share, get Snapshot from Progressive and see just how much your good driving could save you.
So it doesn't actually work quite like that, but you get the general idea. So the better you drive when you have this device, the more money you can save on your insurance. We want to reward safe driving behavior because that's better for everybody. And the people that are not driving safely, well, maybe they deserve the penalty. It looks like this. It's this little device you plug into your car. Very easy to use, but it's evolved over time. So way back in 1998, it was this big metal box thing. You had to get it wired into your car by your mechanic, and it's very difficult to get data off of this. In 2004, it changed so that you can plug these things into the diagnostic port in your vehicle, and then when it collected the data, you're done driving, you plug a cable into your computer that comes out of this device to upload the data to Progressive. And that was kind of clunky. But in 2008, we started working with the cell phone networks. So the device stays in your car, it stays plugged in. At the completion of a trip, it uploads the data automatically. The customer doesn't have to do anything, which is much better. 2010, our marketing team got more involved and they made it shinier. So that was a big milestone for us. And 2014, we introduced these orange stripes on the devices. So here's the blue, here's the orange. Actually, the orange ones indicate these are the ones that track location data for research purposes. So blue means just speed and time. The orange one starts to collect location. We don't use it for scoring yet. We just use it for research to try to figure out what the next variable is. So sort of interesting. 2016, we rolled out a deal with General Motors. So anybody who has an OnStar enabled vehicle, we can score the driving behavior that way if you opt into this program and offer you a discount. So that gets us away from giving devices to people. It's built into the car. And also this year, we're rolling out a smartphone version of the app, which runs on Android or iOS. So you don't have to do anything. I don't have to send you a device. I don't have to mail a device out to you. You don't have to plug it in. You don't have to remember to send it back. You just run this app on your phone, and that's all you need to do, which is very easy. So before Snapshot, before all of this, what did we know about our customers and how they drove? Not much at all, right? We didn't know anything really. All we knew was the year, make, model of your vehicle. Not how you drove it. We knew what you drove, and we can score on that, but that's not very useful. So where did we take it from there? Well, we started collecting speed and time, which is what we do today with Snapshot. This is our current algorithm, our current implementation. It just uses speed and time to plot out this driving behavior. So this is one trip. There's the red dot there is the car. As it's driving, you can see time across the bottom, a trip from about 4 o'clock to 4:13, and the speed of that vehicle. One of the first things we did looking at this is we introduced this concept of speed bands. So depending on how long you're traveling at a certain speed, that can be really predictive. If you're going 80 miles per hour 90% of your time, perhaps that's risky driving behavior. And so we look for these speed bands, and these are just a made-up example here, but we have quite a few more that we use for scoring purposes. Then we introduce time bands, and again, an arbitrary example here, but driving at 3 a.m. on a Saturday morning is probably riskier than driving on a Friday afternoon. Different behaviors, different risk profiles associated with different times of day or days of week. So we score based on that. We also introduced this concept of hard brakes. So each one of these circles here represents where a hard braking event is occurring. You slammed on the brakes and slowed down faster than we thought you should. It was faster than what a typically safe driver would do. And this happens usually when people aren't paying attention. So you're looking at your cell phone or looking out the window or fiddling with the radio, whatever it is, you don't know what's going on around you. Somebody stops right in front of you and you got to slam on your brakes. That's when these happen. The next thing we did is we turned on audible tones. So when a hard brake occurs, we should hear something like that. How annoying is that? That is about the most annoying noise I think I've ever heard, and our customers agree. We've run a test of devices that have that audible tone versus those that don't. The ones that have that tone save 5% more on their insurance because they're safer drivers, because nobody wants to hear that. Over a 2-week period, we see a significant behavioral modification where they stop driving the way that causes those beeps. So it's a very valuable tool. And this is just a simple beep. It's just a little audible tone. We can do a lot more than that in order to inform our drivers of risky driving behavior as they go. So I'm going to try to fast forward this past the beep. There we go. Nobody wants to hear that again. Where are we going next? I gave you a little piece of this earlier today. We started collecting location data. So we started looking at where people are driving, not simply how they're driving. And using this, we can put it in context on a map of here's where you're actually at, which is very valuable information. Looking at absolute speed of the vehicle as they're driving along. Speed 60 miles per hour on a highway is probably safe driving behavior, maybe a little slow, but 60 miles per hour in a residential zone is not safe. And now we know the difference between those two, which is very useful information. We can plot out where hard brakes are occurring. The little red lines in there are where hard brakes are happening along this trip. And so if I have hard brakes in a residential area, maybe that's got a different risk profile than hard brakes on a highway or during a rush hour in urban traffic. Knowing where these occur are useful. We can also plot a heat map here of all high accident areas. So as this person is driving, they have a lot of hard brakes, they're speeding, it's a high accident area. All those things add up to be more risky driving behavior than what a safer driver would do. So we look at all these things. We look at weather data, traffic data, accident data. We layer it into our models. And we come up with the next new predictive algorithm that helps us score our customers more accurately. And we can do fun things like this. So this is stitched together from Google using their Street View. We can look at what that trip actually looked like. We can look at the route. And based on that, we know, was this a blind intersection or not, right? Was there some obstruction around a turn? We can go back and look at the route that they took in order to assess the type of driving behavior. We don't need any cameras to do that. We can use freely available services from Google, for example. So is it big data? Yes. Pavan this morning was talking about how much data we have. We've had over, 2 billion trips. So a trip starts when you turn on your car. Stops when you turn it off. We have a lot of those. Each of those trips generates a lot of data records. That's more than 2 trillion data records. The red is just speed and time of the vehicle sampled at 1 hertz. So we're sampling as you're driving. The purple sliver up there is where we started collecting location data. And we still collect that at 1 hertz, but we collect a lot more data attributes. It's the latitude, the longitude, the heading, quality measures. All that information is what we started collecting there for research purposes in the purple. And that adds up to be quite a bit of data. How many miles have we gotten? More than 16 billion. I don't know the exact numbers right now, but it's more than 16 billion miles. And I want to try to put that in perspective about how big that really is. So does anybody know what this is? It's a probe, right? Voyager 1, it's one of the probes that we launched, US launched back in 1977 or 78. The fastest human-made object ever made, traveling away from the Earth. been traveling for almost 40 years, and we've collected more miles in Snapshot than the number of miles Voyager probe has traveled. And this really speaks to and it gets at the distributed nature of processing this data. So if you have a lot of little devices collecting data versus one working very hard, you can achieve a lot faster. Here's a bonus question. Does anybody know why we see this little wiggle in the blue line? No brave soul is going to venture a guess. The Earth moves around the sun, so it changes the measured distance from that probe that's way out there to where we're at. So it looks like it gets further away and closer. Technology, what do we use to do this stuff? Well, cars talk to our devices, which receive information from GPS satellites sent over a cell phone network into our data center, where we store it in these systems, and we report back out via the web to our customers. So the DBMS in this case is typically SQL Server. The MPP DBMS is Microsoft's, used to be called PDW, Analytics Appliance now, something like that. And of course, we have a Hadoop cluster running in multiple of our data centers, and we leverage cloud pretty extensively for some of our data science work. The tools that our analysts use and our data scientists use are this. A lot of different things that we use there based on the type of user. And we do a lot of visual analysis of this data. So, down from Excel to Tableau to D3, we analyze this data in new and different ways. And the type of users that do this are analysts and our data scientists. So the analysts have the glasses, the data scientists have the pocket protectors, and that's okay. So let's look at the analysts first. What do? They have two main responsibilities. Are our devices happy, and are our customers happy? So does this thing have the right software on it, the right firmware? Is it up to date? Is it working the right way? And do we have enough of them in our warehouse? We don't want 5 of these devices waiting in our warehouse, and we don't want 500,000 of these waiting in our warehouse. We want just the right amount to meet our customer demand. So this is Kristen. She's one of the analysts, and this is the type of work she does. This is her desk. She's got tons of these things sitting there where she updates the firmware on these things and makes sure everything works the right way. And she produces charts like this in Tableau. So this here is the number of miles we've collected for every year, make, model of vehicle. And it's broken down so the size of the rectangle represents how many miles we've collected. Bigger the rectangle, the more miles. Sort of interesting. You see we have a lot of Fords and Hondas and Chevys, Toyotas in there. But we can also look at it this way. So the size represents the number of miles we've collected, but the color represents the number of hard brakes we've recorded. So in this case, a red color means we have a lot of hard brakes, or the amount we're expecting, and blue means a low number of hard brakes. Anything stand out here? What the heck is going on with the Mitsubishis? Yeah, so using tools like this, our big data systems, and then throwing analysis tools and visualization tools on top of it, you can see this stuff. And it turns out, with Mitsubishis, our device was having an incompatibility problem with the diagnostic port on the car. So we're able to reach out to Mitsubishi and get that resolved pretty quickly. We couldn't have done that without looking at the data this way and understanding what's going on. Another thing you can do, voltage fluctuations by vehicle. Each one of these circles is a customer. And the size of the circle represents how many times the voltage in their car has fluctuated up or down. So you want this to be stable. You want it to be flat. But in this case, we have certain customers where we see these big surges or drops. And again, it's easy to figure out. We have these customers that have some problems here. One of these circles, a big pink one near the middle there, is one of our product managers inside of Progressive. And what happened here is his alternator was about to die. So he took his car to the mechanic. He says, yes, your alternator is about to die. He fixed it, and everything's better. Now that we know these type of, this signal indicates a potential problem with a customer's vehicle, we reach out to them proactively. We call customers and say, hey, you might want to take your car to a mechanic. Your alternator could die. We don't want you to get stranded anywhere. And at first we thought it'd be a scary big brother thing, like why is my insurance company calling me and spying on me? But they're actually very happy and receptive to this, because we're looking out for them and trying to take care of them here, and they appreciate that. So good success there. So what about our data scientists? What do they do? How do they use these systems? 2 main things. Is our algorithm accurate? And how can we improve it? So these are the people that are doing this brainstorming, coming up with the next new thing, right? The next big thing, how can they leverage this data set in a new and innovative way? This is Edward. He's one of our data scientists. And he's using a nice tool here that helps him analyze some of this driving data in a little bit different ways. So it's this big touch screen, and he's looking at weather data and traffic data on one side, he's got speed on the other, he's analyzing the data a couple different ways, and just having this tactile, very interactive type of data exploration, he came up with 15 other ideas that you want to test out in about 10 minutes. So putting these tools in the hands of our data scientists and analysts really help us come up with new ideas and analyze our data sets. Here's something that he's done. So here's every snapshot trip we've collected. The red in this case is a lot of data, the blue's a little bit of data, and this is just a plot of where we've collected data since we started. So anything stand out here? Anything look funny? Okay, who the heck's driving in the water? Right? We have personal watercraft insurance and we have usage-based insurance, but we don't combine those two. So we shouldn't see cars in the water. And so to understand what's going on there, first you have to understand how GPS works. So space, the Earth, we're somewhere on this thing, right? Somewhere on this globe. And these are a constellation of GPS satellites. There's 24 of them that orbit the Earth in 6 different paths. There's 4 in each path. They each cross over the same point in the Earth about twice a day. Sort of neat how that works. Again, things that were launched back in the 70s that do great things. This is the constellation. This is what it looks like if you were just to see the paths of these things. But we want to prove that we are indeed here. We're here in San Jose. So how do we do that? Well, with one satellite, we can time the radio signal from where that satellite's at to us. And based on the timing, the very precise timing of the atomic clock, we know how far that signal's traveled. And given that, with one satellite, we know we're anywhere on this red sphere. So that's kind of useful, but not very useful. If you include 2 satellites, you get the intersection of those 2 spheres, which is a circle. And we know you're at any point along that path, which is kind of better. 3 satellites gives you 1 of 2 points, either at the one at the top or at the one at the bottom. And unless you are an astronaut, we can get rid of that. And now we know here you are. So 3 satellites gives you that exact precise location. In most consumer grade GPS, there's actually 4 satellites that are used. The 4th one gives you altitude and a little bit more precision, but 3 is good enough to get the point across here. What can go wrong? Dilution of precision. So we're this dot in the middle. We're timing the signal from these satellites, and we have perfect quality. So this is an ideal situation. So as we're driving around here making this figure 8, we have this great clean reception. We got this nice, smooth, hypnotic thing. Nobody falls asleep here. But as quality degrades, it gets a little bit rougher, and there's uncertainty that's introduced in that signal. So now we're down to 50% certainty, and this is what the data looks like when it comes through because we don't have clean signals from the satellites. That jaggedy path there, that's what the data actually looks like if we were to plot it out of our driving data. We know customers aren't driving like this, we hope. We hope they have that smooth path, but this is what we have to deal with when we bring this data in. So what causes this? 2 main things. One, mountains can bounce this signal around. If you're standing next to a mountain with a GPS device, if the signal can't get through, then you've lost visibility to satellites, and so you have less data to work with. Or if the signal gets bounced off that mountain and then to you, the distance changed as you're timing that, and so it gets confused as to where you're at. The other thing it can be is buildings, highly urban locations. So down in here in Manhattan, that signal gets bounced around through the buildings, and it's really hard to get a good GPS lock, and so we see problems there as well. So let's start with the first one, the mountains and all that stuff. Here's every trip. Again, we've seen this. And the first thing we can do is clean this up. So let's identify those straight points. If you're going along on a highway, point along this highway, and all of a sudden there's one point that's way off in the Atlantic Ocean, and then you come back and it's still point along that highway, we can remove that straight point. We know you didn't do that. That was a glitch. So removing that gets us a lot cleaner, but it's not perfect. So doing that initial filtering, just a sanity check, helps get our data set a little bit cleaner. So what does the quality look like, though? The overall quality of this data. We can plot that out. Our devices have a chip in them, one of these in here, if you want to come up and look at these things, that reports the quality of the GPS signal. So how many satellites can I see? What's the dilution of precision, the HDOP, VDOP, all that stuff. We get that, and you can plot it out. So here, red is low quality, bad. Blue is high quality, good. Anybody see any patterns there? Mountains, yeah, right? So mountains. Let's look at altitude. We can plot out altitude from the devices. We receive that as well. Red's high, blue's low. You see that the Appalachian mountain range there. You see a lot over here in the west where it's a higher altitude. And we can fade between these two and see how they line up. And it's not quite right. It's close, but it's not perfect. So over there near the east, it doesn't quite line up. In the west, you just have this high altitude area, but the signal is a little bit noisy throughout. And if we do this visual comparison where pink and those bright colors are where there's disagreement, dark is where there is agreement, you want to see this almost totally black. If it's black, it means it's good agreement. We don't see that here. And if you plot it this way, of GPS quality versus the altitude, we're looking for a correlation here. We want to say as the altitude increases, the quality decreases. You'd expect a line on the diagonal here from that bottom left corner, and we don't see that. We just see noise, right? We see we have a lot of customers around 400, 300 feet above sea level and some higher up. So that's not quite what's going on. What else can we try? What about the change in altitude, the variance, right? So here's altitude variance plotted out. And what this means is I'm not standing up on this high platform, this plateau. It's that there's a lot of changes in altitude right around me. So how much change in elevation is there within a given square mile area? We call that variance. And if you look at that and overlay that one, it's a bit more lined up, right? It's not that I'm at 3,000 feet above sea level. It's that it's changing quite a bit all around me, and I have these obstructions. Visual difference is better because it's dark and you can barely see anything. Here we're starting to take a little bit more shape. We would like a nice linear curve here, but we don't quite see that. But it's getting a little bit more conical, which is better. Not perfect, but it's getting there. So that was the big geographic stuff. But what about the urban stuff? Mountains and tunnels and all that fun stuff. Anybody know what this might be? Looks like something my kids drew and put in my refrigerator. It's driving data, right? This is driving data we received. This is what it actually looks like if you just plot it out raw. Each one of these squiggles here is a different trip one of our customers has taken. And we can put this on a map and see what that looks like. And they're driving through buildings and like all this crazy stuff going on. And we know they're not really doing this, we hope. Otherwise, we got bigger problems. But they're not doing this, so what's going on? Anybody know what city this is? It's kind of hard to see from here. But we want to come over in Washington. This is actually Seattle. So the Washington State Convention Center is right there. And the data, remember, looks like this. And that's because Convention Center over the freeway. Yeah, exactly. The Convention Center goes right over the I-5. So you've got 8 lanes of traffic that go right underneath this huge concrete building. No signal's getting through that, and it gets bounced around. It's all crazy. And the output looks like this. It's a mess. So we see this everywhere. We see this everywhere across the country. So here's the big macro view of Seattle. We're going to zoom out a little bit. We'll plot our data on top of that. Blue is good, high quality. Red's low quality, and it still looks terrible. And like, what the heck is this guy doing driving in the water? The ferry, yeah. There's a ferry that goes out to an island. And so what somebody did is they parked their car on the ferry. They left their car on, so the wheels aren't turning, but the GPS signal's changing. So we say, hey, this car is moving, but it's not really moving. So how do you score that? Is that safe driving behavior? Is it forgetful driving behavior? What do you do with something like that? So we got to clean that up. We got to figure out how we score that stuff. So here's an example. Here's one trip. This is one person. They're going to get on the I-5. They're going to head south. Blue's high quality, red's low quality. You should be able to pick out pretty easily when they go underneath that convention center. The signal just gets crazy. Right, there it is. It looks like they jumped over a couple blocks and it completely drops out. So it gets bad. But here's a chart that shows the time of that trip along the bottom. The quality on the other side, you can see it dips down when they reach that point. So this is what the data looks like raw when we get it. But after our data science team works on it, it looks like this, which is much better. So animating between the two, we can see that, yes, we have some pretty advanced techniques in order to clean up this data and make it usable, because we want our customers to have confidence that we're scoring them based on realistic driving behavior. If we showed them this madness type squiggly stuff that's going on, it's not a good customer experience. So after we've applied our data science techniques to clean all this up, it looks like that nice clean map there. So another example. This is Las Vegas. This is well, one night's worth of trips sped up a little bit. Each one of these is a different trip as they're driving. And from here, you can see it's kind of an organic thing. It's neat to just watch. You see people driving out to the desert and all that. I don't know if that's like gangsters getting buried out there or something, but you can imagine like what sort of crazy stuff is going on at 4 in the morning when people are driving around the desert here. And if you just pause it, you can look. Here's everything at once. Red's high volume, blue's low volume. We can also look at quality. Red is low quality here, blue is high quality, and you see these blips near the middle where we have low quality. We pause it and look at it like this. If anybody's been to Las Vegas, they know what's going on here. So if we zoom in a little bit, you can see, yeah, it's the Strip, right? You're driving next to these tall buildings and your signal gets obstructed, and so that's what's going on. And you can't blame Donald Trump for this one because his building's further off the Strip, but other buildings do it. So we learn from all this. Data's awesome, right? That's why we're all here. We're all data geeks. Messy data is also awesome, and it teaches a lot. We learn a lot from the errors in the data. And visualizations help you make sense of it. We do a lot of visual data exploration at Progressive, and it helps us understand what we're looking at. It gives us insights into what we want to do next, and it lets us know when we get it right. So as we're applying our data fixes, as we're doing all of our updates, we want to make sure we're getting the right end user experience here. What's it mean to Progressive customers? You saw something similar to this morning. This is the amount of discounts we've given out to all of our customers since we started Snapshot. It's a lot of money. Right? This, again, it's not some little experiment that we're running. We're fully invested in this. It's $563 million when I last checked at the end of the month. So it's big money, and it makes a huge difference for our customers. Questions?
Yeah, so I noticed California was just blank. Is that because it skipped?
Yeah, California, North Carolina, they do not have the Snapshot program right now. So we're a highly regulated industry, and each state has different regulations and rules, and we don't run Snapshot in those two states. Not yet. I'm doing great on time. We've got 12 minutes for questions.
Have you guys taken this data and related to like losses, accidents, or?
Absolutely. So the question is, do we use this data and relate it to losses and accidents? That's exactly what we do. So all this modeling that we do, all this data we collect, we're optimizing this against our premium and loss data. So we want to find out what certain behavior indicates a higher risk driver. And we identify a higher risk driver based on the amount of money that we pay out in claims, or the amount of money that we need to service that policy. So all the modeling we do, it's tuned against that risky behavior, which is how we measure premium and loss. So yes.
In your earlier presentation, you commented on reducing compute memory storage, and that you helped them solve that problem. Going to this model, how did you guys make the processing more efficient?
The question is, how do we make our processing more efficient? We had two main problems to solve. One was in our analytics space, so it's just analyzing the data, figuring out what's next. We couldn't get a lot of our big jobs done. And so that's when we leveraged a lot of the technology from Hortonworks and built out our data center and used the cloud to do a lot of this work. What I like to tell the story is, right now we count the number of hard breaks. And the number of hard breaks is very predictive. So if you break 5 times on a trip and I break 10 times on a trip, on average, I'm probably a worse risk. But what if the next big thing is the number of left turns that you take, or something like that? Just come up with something. We got to go back and we got to look at all the data we've ever collected. We've got to run over the entire data set to compute the number of left turns, and then see what sort of correlation there is to our losses. And so as we're collecting more and more data as we go on, we want to be able to see, when we come up with these new ideas, are any of these things predictive? And it's actually the older data that's the most valuable. Because if I was driving 5 years ago with Snapshot, after that I've got 5 years of data, and I've got 5 years to potentially get in an accident or not. So the oldest data is most valuable, so we have to keep everything and analyze everything. So to optimize that analytics process, we leverage a lot of cloud resources. We leverage Hortonworks to do a lot of our big data number crunching. And we get these aggregates down. So I count how many left turns you take, and then we use different technologies, such as I listed before, SAS and R and H2O to analyze those aggregates and see how predictive they are. So we brought in that stuff. Yes?
So the visualizations are awesome. What tool did you use to generate those?
Question is visualization tools. Most of what you saw here today is D3. The presentation framework is called Reveal. It just runs in a web browser. And the visualizations inside of it were all built with D3, which is a free open source JavaScript library.
Also, I have another question. So you're capturing the time and the location. Sometimes the weather also makes an impact on this analysis. Like you like merge the weather data.
The question is, do we use weather data? Yes. We use it quite a bit actually in our loss reserving. So how much money should we set aside for the next hurricane that's going to come? We use it a little bit for research purposes in usage-based insurance. So not as much here yet, but more in our core insurance practice. Yes?
So do you provide some sort of feedback to the customers regarding their driving habits? You know, some sort of proactive thing. Like maybe they haven't gotten in any accidents, they don't have any tickets, but you just let them know, hey, they did the following things.
Yep. Question is, do we provide any sort of proactive feedback to customers? Well, you heard the annoying audible tone, so you get that. But we do produce reports that show for each trip, here's the speed that you were going, here's the risky times that you're driving. So they do get reports at the completion of a trip so they can adjust their driving behavior. As we move over to using smartphones as a device, we hope to give more actionable feedback real time as they're driving or at the completion of a trip, instead of them having to go to a web page and pull up their trip data.
So the follow-up question to that is to provide some sort of anonymized data to municipalities to help them identify, well, you know, however they've signed the road signs or constructed the roads, because a lot of, you know, accidents go up for more than just bad driving, sometimes it's bad road signs. So.
Yep. Question is, do we share data with anybody? The answer is no. So our terms and conditions state we will not share your data with anybody, and we don't. So we don't share it with government, other companies, anything like that. The only time is when the lawyers get involved. If there's something interesting going on with a claim, then we have to. But otherwise, we don't sell the data. We don't give it to anybody. It's a key asset for Progressive.
How many nodes are you running in Hadoop, and what are your plans to move to the cloud?
Hadoop nodes in our primary data center, we have about 60 that runs this piece of the system. Secondary cluster in a different data center has maybe a third of that. In the cloud, we scale up to hundreds, quite a few hundreds. And that's usually for our bursty type workloads where analysts want to run some big sort of query to get aggregates. They'll spin up a few hundred nodes in the cloud, run their analyses, and then decommission it, bring the results back on-prem.
You're not storing any data in the cloud at all?
We do push data to the cloud to do our analysis, and then we pull it back. Yes?
So do you use Hadoop or the Hadoop for other stuff than telematics?
Yes. So the question is, do we use Hadoop for other things? Yes. Actually, Progressive is one of the top 5 advertisers in the United States. You see Flow everywhere and all that. And what makes Progressive different than other firms, a lot of times people just give a big bundle of cash to a marketing agency and say, go make good decisions based on this. We do all of our analysis internally. So where we place our ads, how effective they are, what websites, TV, all that stuff. We do all that analysis internally. So we use Hadoop to do a lot of that. There's quite a few other use cases. Claims, we do a lot of analysis of all of our claims there in Hadoop. We have decades worth of claims information that we do this rich textual analysis on, natural language processing to figure out what did the claims adjuster write about this vehicle, about this accident, and we can trend that and identify interesting patterns there. So we do use Hadoop quite a bit of other places. This is just one of the fancier ones that we like talking about. The question is, do we analyze the driving data after an accident? So we've tried, and there hasn't been enough occurrences to look at this telemetry data as an accident occurred or when it occurred. So 1 Hertz isn't usually good enough. to capture a lot of what happened, to recreate an accident, and we don't have enough customers on it to get good coverage. So we've tried, we've looked at it, but we're not quite there yet.
How big is your data science team?
Data science team, we have several. So we have data scientists that are aligned to different business areas. And in the Snapshot area, we have 2.5, and I think it's pretty lean. So we have some very talented people that work really hard on the data science team for Snapshot. Other areas have larger teams. In claims, I think it's about a dozen. So different business areas have different amounts, but this one's a little bit on the smaller side.
What are the main features do you use for your insurance model?
I'm sorry, one more time?
What are the main features of drivers do you use for your insurance model?
What features of drivers do we use for some of our insurance models? Hard braking is interesting. That's a feature, right? We count that. What's actually sort of interesting is if you speed, you're actually a safer driver. So this just stays with us, right? We're friends. It doesn't leave the room. Yeah, so if you're pacing traffic, which is generally faster than the speed limit, there's less passing going on, there's less interactions, and it's safer behavior. So the people that are going 40 miles per hour in a 65 miles per hour zone, they're a much higher risk. And so we see these interesting insights about if you're going slightly faster than the speed limit but pacing traffic, that's much more safe driving behavior than being 20 miles per over, 20 miles under. So we look at speed, we look at time, we look at acceleration. These are the core features of driving that we analyze. Some of the external stuff with location data, we haven't brought in a production version yet. We're just doing it for research. Does that answer your question?
How much did the snapshot increase the Gini of your model?
How much did Snapshot increase the effectiveness of our model?
The Gini value of your model.
I can't answer that. Sorry. If you want to talk afterwards, we can talk about it. But it's, as I showed in the keynote, it's 2.5 times more predictive and valuable than everything else we have.
So my question is, how does the underwriting team take advantage of what you guys do?
How does underwriting take advantage of what we do? You might look at something like somebody says their vehicle is garaged at this certain address, and yet the snapshot data shows they've never been there. Why? Right? So is this a fraudulent type behavior? Maybe they actually live in New York and not New Jersey. Now you can tell the difference between those two. So we might do additional analysis or follow-up on certain customers if we see this strange behavior that doesn't match what they're telling us. So there's some other use cases where we use this for underwriting, but that's a big one.
For say for each drivers, I guess you guys should have some system recording their like a credit score or something like that, similar to that, right? So basically, your analysis proceedings might be very likely to be incorporated into the rating, right?
Question is, how do we use Snapshot and rating?
Right.
So when you sign up for a policy, you can get Snapshot. We'll give you a discount as soon as you sign up, just a discount to participate. And after a 6-month period, we can offer you a discounted rate based on your driving behavior. Or if you're a bad driver, we might give you a rate increase, up to a 10% increase if you have bad driving behavior. And those people usually don't stay with us. They go to our competitors, which is exactly what we want. So I think I'm out of time. If you want to come up afterwards, I'll gladly talk with you. Thank you.